Hello and welcome to Anthrax. In today's video, we are going to talk about temperature stresses, and later on we'll be solving some simple problems on it. So first of all, let me take two cases on what to explain what is temperature stresses. So first of all, in the first case, we'll go with a rise in temperature by 3 degrees Celsius. Right. So I'll call this. We already know that if the temperature rises, the material expands because of thermal expansions. Right. So if the material expands, I'll call this strain because of the rise in temperature as epsilon T, and that would be given by alpha into T. That is the rise in temperature. Here the alpha is thermal coefficient of thermal expansion. Right. So I'll call this length as A, and call this breadth as B, and I'll call the depth as D. Right. So now if I want to calculate the change in length, I'll have delta A by A, that will be equal to alpha T, and delta A will be equal to A alpha T. And similarly for change in breadth, delta B is equal to B alpha T, and for change in the third dimension, that is delta D is equal to D alpha T. Now let's say this particular prismatic bar is not constrained in any of the direction. So this bar is free to expand in all the three directions. If it is free to expand, there will be no stresses for this. But if we have something like this, if a bar is on a fixed rigid joints or rigid ends, which is not free to expand, then because of the rise in temperature, this particular bar experiences compressive loads. So I'll call this as sigma C. Right. So this, I'll call this as A and B, and we know that because it is a rigid joint, delta AB will be equal to 0. Now what is this delta AB is given by? This would be given by the change in length because of the thermal expansion and because of the thermal stresses. Right. So this would be nothing but L into alpha T, and if let's say if the length is L here, L alpha T, and minus, since it is a compressive load, so our compressive stress, this will be minus. So sigma into L divided by E, that would be equal to 0. Now I can call sigma, if I rearrange this and equate sigma, I'll have E alpha T. So this is the stress developed due to the rise in temperature. Right. So coming to the next case, because of the drop in temperature, let's say I have a similar bar on a fixed joint, let's say, and if the temperature drops, the material will contract, because since it is in a rigid end, this is not free to contract. So now this bar will experience a tension force, right? So this would be the sigma. Now here again the same thing. Let's say if the length is L, and I'll call the ends as A and B, the total delta AB will be equal to 0. Now the delta AB will be given by first of all, if this particular bar is free to expand, what would be the change in length? So that would be given by L alpha T. So this would contract, right? And now since now if the bar is fixed, now the bar is fixed, now if this bar experience tension force, will have plus sigma L by E, and whole of that will be equal to 0. Now here sigma will be again be equal to E alpha T. Right. So with this prior knowledge, let us move on to the problems on this temperature stresses. Right. Now a steel bar 2.5 centimeter, 2.5 diameter, I'll call this as D is equal to, I'll make sure everything is in mm square or mm. I'll have this 25 mm diameter, is rigidly attached to two parallel support 5 meter apart. I'll draw a schematic. We'll have two rigid supports, okay, and the length of this rigid supports is 5 meter. Okay, find the pull exerted by the bar on support when the temperature is increased by 100 degrees Celsius. So this is the rise in temperature. So the bar will experience compressive forces. So the first case is if the support do not yield, meaning that there is no expansion in this element. So we have a rigid support now, right? So now let me take the first case. I'll call this as case A. Now delta AB, I'll call this as A and B. Delta AB will be equal to 0. right? So delta AB is again given by L alpha T minus sigma L by E, and that would be equal to 0. Now sigma is given by E alpha T. I can directly find out F directly, right? F is given by sigma into area, right? So I'll substitute the value for sigma, that is nothing but E alpha T into A. Now which is nothing but E is given by 2.1 into 10 to the power of 5 Newton per mm square into the alpha is given by 12 into 10 to the power of minus 6. I'll have 12 into 10 to the power of minus 6 per degree Celsius into the rise in temperature 100 into the area, which is nothing but pi by 4 into 25 square. So which is nothing but 123.7 kilonewton. So this would be the pull exerted if the ends are rigid. So now we have case B. So now what does case B say? Case B says that if the yielding of the support is 0.25 mm. So I'll draw a small schematic for this again. Right, so this would be the initial support. I'll call this as A. Now this yields by 0.25 mm. Sorry, 0.25 centimeter. Right, so now in this case, the delta AB is not equal to 0, but instead it is equal to 0.25 centimeter, that is nothing but 2.5 mm. Right, so now again I'll apply the same formula here. Delta AB is again given by L alpha T minus sigma L by E, that would be equal to 2.5. Now let me calculate the value for sigma. Now the L is given by 5000 meter into alpha. Alpha is 12 into 10 to the power of minus 6 into rise in temperature is 100 minus sigma into L is 5000 divided by 2.1 into 10 to the power of 5 is equal to 2.5. Now here if we simplify this, we'll get 6 minus 0.024 into sigma, that would be equal to 2.5. Now this in turn the value for sigma is 145.8 Newton per mm square. Right, now to calculate the pull, we'll have F is equal to sigma into A, which is nothing but 145.8 into pi by 4 into 25 square. So which is nothing but 71.5 kilonewton. Right, so let me move to the next question now. Right, so a bar of cubical shape of length L is confined in all the directions between rigid supports. If the bar is heated uniformly by T degrees Celsius, then find the force exerted in any direction. So again I'll have to find out the force. So here we have a cube. So I'll draw a small schematic for this. So I'll not show this rigid supports here, but let us understand that this is not free to expand in any of the directions. If it is not free to expand, it experiences compressive stresses in all the three directions. All the three directions will have sigma because it is uniformly it is heated up uniformly. So I'll call the directions as x, y and z. Right, so now I'll only consider the direction in as x, because if I find out any one of the direction, all the directions will experience same pulls. Right then, so let me only calculate the delta x. Again that will be equal to 0 because it is rigid end. Now this again would be again given by L alpha T, and now in the x direction it will experience compressive load minus sigma L by E. Now because of the compressive stresses in the other direction, which is y and z direction, the x direction will experience some tension force, the lateral strain, right? So that is plus nu into sigma L by E because of the y direction, and plus nu into sigma L by E because of the z direction. So I'll not specifically mention sigma x, sigma y, because sigma x is equal to sigma y, it will be equal to sigma z because of the uniform T. Right, so all of this again will be equal to 0. Now if I take L alpha T minus, I'll take sigma L by E as common, I'll have 1 minus 2 nu will be equal to 0. right? So now if I calculate the value for sigma, sigma will be nothing but E alpha t divided by 1 minus 2 nu, right? So now what is the pull? uh, the force exerted will be equal to sigma into A, so that is nothing but E alpha t into A divided by 1 minus 2 nu. So A for this particular cube is nothing but L into L, so I can write this as E alpha t into L square divided by 1 minus 2 nu. So moving on to the next question. So we have a square plate of size L into L rigidly held between three edges is free to expand along the fourth edge as shown in the figure. If the temperature is increased by T degrees Celsius, find final expansion along the fourth edge. So now if I take the direction as x and y, sorry, as x and y, so we'll have to calculate delta x, right? So here, first of all, will there be any stresses in the fourth direction, in the x direction? So delta x will be equal to 0 because there is no fixed end. So this material will be free to expand in the x direction, therefore the temperature stress in the x direction will be equal to 0, but in the y direction it is not equal to 0 because it is rigidly fixed, right? Then so again, if I want to calculate the delta x would be given by L alpha t minus sigma x L by E plus, again it will experience compressive load under y direction, so it will be elongated. So here elongated along x direction plus nu into sigma y L by E. So this delta x is again 0. Now L alpha t plus nu into, if I substitute the value for sigma, that is nothing but E alpha t into L divided by E, and again E will be cancelled out, so the remaining thing is delta x will be equal to, I'll take L alpha t as common, L alpha t into 1 plus nu. So this will be the total expansion in the fourth direction or the fourth edge. So moving on to the next question, I have a bar AB of length L is held between rigid supports and heated non-uniformly in such a manner that the temperature increases delta T at x from A. So if I have, I'll call this as x, and the expression of delta T is given by, I'll simply write this up, delta T is given by delta TB into x cube divided by L cube. So delta TB is the temperature at the support B. Delta TB is the increase in temperature at B of the bar. Derive the formula for compressive stress sigma C in the bar. Okay, again I'll have to calculate the stress here, right? Now if I write a free body diagram for the element, I'll take an element here of length delta x, sorry, dx. So if I take an element dx, let's say if the length of this element is dx, now this would expand by, let's say, delta x because of the rise in temperature. With this knowledge, let us start solving the problem, right? So first of all, delta AB will be equal to 0, that we have in the one end, and I'll only take up delta x now. Now delta x, the expansion of this element, what does that give me? That gives me the length, that is dx, into alpha into t into t. So I'm talking about the free extension of the element, so that is nothing but dx into alpha. I'll substitute for delta t, that is nothing but delta tb into x cube divided by L cube. Now for the free extension of AB, so to do that I'll simply have to integrate this, integrate from limits 0 to L alpha delta tb divided by L cube into x cube into dx, so which gives me alpha delta tb divided by L cube into x to the power 4 by 4 with the limits 0 to L. Now the total free extension is given by alpha delta tb into L divided by 4. Now we know that since the bar is fixed end, delta AB is equal to 0, and now if I substitute in this, we'll have L alpha TB by 4 minus sigma C L by E, and that would be equal to 0, right? So this is the free extension minus the extension because of the thermal stresses. Now sigma C is given by E alpha delta TB divided by 4, and this would be the total compressive stress because of uneven temperature rise. Let me move to the last question in this video. Again, we'll have a copper bar AB of length 2 mm, 2 meter is placed in a position at a room temperature with a gap of 0.25 mm between end A and the rigid restraint. Okay, I'll have something like this. I'll have a bar, I'll have A and B, and we have a gap of 0.25 mm here with the rigid support. So here one of the end is rigid, so we'll have 0.25 mm here, and the length is 2000 mm. If the bar rises in T is given by 100 degrees Celsius, alpha is given here, and E is given as 10 to the power of 5 Newton per mm square. Now what do we have to calculate? Calculate the axial compressive stress sigma C. Now again we'll go with the same rule. We'll have delta AB. So delta AB is not 0. Here it will have 0.25 mm. I'll substitute the formulas for here. First we'll have the free extension, that is L alpha T minus extension because of the thermal stress, because sigma C L by E, that would be equal to 0.25. The length is given as 2000. The alpha is given as 18 into 10 to the power of minus 6 into the rise in temperature is 100 minus sigma C is given as, oh sorry, that is what we have to find out, into the length is 2000 again divided by 18 into 10 to the power of minus 6, that will give us 0.25. Now if I simplify this, I'll have sigma C is given by 167.5 Newton per mm square. Thank you for watching the video. Hopefully this has been helpful for you. Please like, share and subscribe. Thank you. Happy learning.